Alright guys, in this video today we're going to be looking at one of the building blocks of calculus, which is the derivative essentially. What we're going to be looking at is the tangent to a curve, the slope. Okay, now in class we were looking at x equals 1, so we were trying to find the slope of the line instantaneously at that point when x equals 1. Now in order to do that, we said, well, we could just draw a tangent line. But again, if I draw a tangent line, I could draw it something like this. I could make it a little bit steeper. And with a hand-drawn graph, it's a little bit tough to tell exactly where that slope is. So what we're going to do is we're going to do what we talked about in class, the secant. And by using the secant, and by using secants that get progressively closer, then we'll be able to get a little bit better idea of what this slope should be. So let's go ahead. We're going to draw a secant from x equals 1 to x equals 4, just as an example. And so the slope of this line will be approximately equal to the slope of the line at 1. Not exactly. In fact, it'll be quite a bit off, but it'll give us a starting place. So we'll use that one. Of course, to get slope, we do y2 minus y1 over x2 minus x1, or the change in y divided by the change in x. So that would be 10 minus 2.5, which is 7.5, over the change in y, which is over the change in x, which is 4 minus 1. So that's 3. So we get a slope of 2.5. All right, now I'm going to do the next couple really fast. Our next one is going to go into 3 and then 2. I'll do those two right now. You can go ahead and check it on your own, but I don't want to take up video time for that. So here we go. All right, that was quick, huh? Now, I took the liberty of adding a couple more points. You'll see this point right here takes in the 3, 6.5. This one is the 2, 4, so those are the secants. And then I went ahead and I did a couple more that went to 1.5 and 1 1/4. So I'm getting closer and closer to my 1, 2.5, shorter and shorter secants. All right, and I went ahead and put those in. I calculated those. You can double check my work on that. But you can see that the slope is getting smaller and smaller and smaller, but in different increments. And so you can probably guess that there's going to be some type of place where eventually you're going to stop, right? You know that it's going to have some type of limit as the slope gets closer and closer and closer to whatever the tangent slope is at 1, 2.5. Now I use that word. We talked about this in class, that when you get closer and closer and closer to something without quite ever getting there, that's what we call a limit. Now, what are we doing when we're finding the slope here? Well, really, we're taking f of x, and that's some x that we don't know, right? They could be the second secant line. And then we're going minus the original point, which we're going to call f of a. And then we're going to divide by x minus a, right? And so this x comma f of x, that's my second point. And then f of a, right, is going to be whatever point I'm at. And so this right here would actually give me the slope of the tangent line for any secant line, right, for any given x. Now what we want to find is we want to find the limit of this as x approaches. So we want x to get closer and closer and closer to a without ever getting there. So what that does is it gives me a secant that gets closer and closer and closer and closer and closer, smaller, 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 all the way to 1, 2.5, but won't ever quite get there. So I'm getting closer and closer to this point without ever reaching it, and that's the definition of a limit. And so essentially we can say that the slope of any point on a curve is equal to the limit as x approaches a of f of x minus f of a over x minus a. All right, that same thing is shown in your book, but this is the basic definition of a derivative. All right, go ahead and look at the next one, and we'll look at the integral.